Okay, I'll start again. Today we'll be working on GPT and Bert, and the GPT model has to predict the next tokens based on the previous sequence of words. So we'll be using, based on our last transformer lab session, we'll be implementing a mini GPT from scratch and training our model using our data set. Okay, I need to mute everyone, so. Everyone's muted, and for Bert, we will take a pre-trained model from Hugging Face, and the Bert is a pre-trained model, and we can apply mask language modeling and next sentence prediction. So using our Bert model, we can it's trained on MLM and next sentence prediction. So today we'll be working on these two. First of all, check your runtime type. It should be on GPU. You can install all the required setups here. And import data sets and torch. Today, for GPT, for training the GPT, we will build our own decoder-only transformer model, and we will train it with ELI5 dataset. So please load these datasets. ELI5 is a long-form question answering dataset, and we're only going to use the long answer part without the question, and we're going to put in the answer we're going to generate the next word for the answer text sequences. And for train, we're going to download 50K, valid 2K, test 2K. So using this load dataset function, this dataset actually has a bunch of open source datasets. So you can pull whatever dataset you want using this function. And now if you've loaded your train valid test set, we'll be storing it into a dictionary. And if we look at our ELI train, we can see it's wrapped in a dataset class and it has these kinds of features. So when we pull this dataset, all these features are pulled for each data sample, and we have 50K data samples. And this answers text, it's in a nested form. So this text is within this answer key. So we can access the answer part using answers text. And when we load the first data sample for the answers text, we get this data sample. And we're only going to use, as I said before, we're only going to use the answers for generating text and training our model today. So this flatten function, because the answers text is in a nested form, we're just going to flatten it using this flatten function. And now when we look at our dictionary, it has answers.text and it's not in a nested form. So here we're gonna take a pre-trained tokenizer and we're gonna build a pre-process function here. So for the tokenizer, when you're using a pre-trained model and when you're fine-tuning that pre-trained model, it's very important to match the model for the tokenizer and the model for the pre-trained model. So you need to use the exact pre-trained model tokenizer when you're fine-tuning a model. However, today we're building a model from scratch and training our transformer model, decoder-based transformer model from scratch. So we can actually use any kind of tokenizer here. But it's important to remember that when you're using some pre-trained models such as GPT, you should always you should always use the tokenizer for the model because it was trained with this tokenizer in the pre-trained stage. And for this pre-process function, you should, it's a very simple function that joins all the sentences and for each data sample and tokenize the joined sentence. So it returns a tokenized result for each data sample. And I'll give you maybe 3 or 5 minutes to implement this function. What do you mean by function signature? In the chat box? So for the input, it takes in the answers.txt. And for the output, it generates the tokenized output. So you can put it into the tokenizer function. So this function is a very simple one. You can put in the answers.txt part, which we are using for training our model. And we can join the answers.txt so that it is put into a single sentence. And we can put it through the tokenizer. Okay, and for this part of code, we will loop through the train valid test data sets, and we will apply this preprocess function. And we can loop through each data and apply this function using this map function here. And then this batched equals true means that we will apply this function in multiple batches in parallel and with 4 number of processes. So you can try running this code. You don't need to care about these warnings because first of all, we're not using the pre-trained model. And second of all, we will split the sequences into maximum sequence length that we define later in our code. Explain the data. So we're using this ELI5 dataset, which is a long form question answering dataset. And we're pulling it through this load dataset function. And we're just gonna use the answer part, which is a long text form, and use it to train our model. If we run this code, we can see that our data set is tokenized and it has input IDs, attention mask for each data sample. And the number of data samples are 50K. And then if we access the first data samples input IDs, we can see that the train data that we want is the text is tokenized into this index format. Okay, and for the block size, we're gonna set a maximum sequence length for our training and train valid test data so that it fits into our GPU. So we're gonna first concatenate all text for each data sample. So if this is in a nested format, for each data sample, we're gonna concatenate all the sentences in each data sample into a single list. And then we will get the total length of the input IDs. So this list, this part, it equals to input IDs key. And if we access this input IDs data, we can compute the length of the total input ID tokens. So for this part of code, we will split our um, input ID sequence into our maximum sequence length defined here. So we will split it into 128 tokens. So that this 128 is the maximum sequence size. And we will add begin of string token and end of string token on each end. And for the input IDs, we're putting it between these tokens. And we're only putting 126 because when we put these special tokens on each end, this sequence length would eventually be 128. So you can run this code and we can also apply the map function with this group text for each train valid test data. And it applies this function in batches. So if we finish processing this root text, we would get this result. And so the input IDs are split into maximum sequence length for each data sample. And we can access the fourth index data here. And so this code here, it simply puts all the sequence of input IDs into a list so that it's easily accessible. So I'm just appending all the data sequences for each data sample into this result list. And this I input IDs consists of chunks of 128. Okay, so we can see that our trained data size is, our trained data shape is like this, which with our maximum sequence size 128. And we can try decoding our encoded input, which has this begin of string token in the front and the end of string token, end of text token in the end. So for different tokenizers, we would have different EOS and BOS tokens. And for this tokenizer that we're using here, the BOS and EOS are both end of text. Now we're going to start building our causal language model. And text generation is basically done using GPT-based models. And it's a decoder-only model with which predicts the next word using the previous sequence of words. And for GPT, it doesn't have it's a decoder only model, so it doesn't have an encoder. So that's why in our last transformer lab session, we had our full transformer with both encoder and decoder. But for this causal language model here, we're only going to stack the decoder blocks and build a decoder only transformer model. And that's why we don't need the encoder decoder attention part in our decoder layer. And we're going to modify last week's code so that we would only build a decoder based language model. So import torch. And this multi-head attention part is same as last week. And also this position-wise feed forward class 2. You can run all these 3 codes, which are same from last week. And then this decoder layer part is different. So as we can see here, this is the decoder layer block. This is a single decoder layer block, and it has masked self-attention feed forward network without the encoder decoder attention part here in the middle. So from last week's code, we can eliminate the encoder decoder attention part, which should be between this fully connected and masked self-attention part. So you can run your decoder layer. And for the decoder class, we don't have cross attention scores, so you can eliminate the cross attention scores part and only return the decoder layer output. So now you're gonna have to use all these classes defined above and build the decoder only GPT. So I'll give you 5 minutes. You can reference from last week's transformer code, which is on Causal. Okay, so this is the code for GPT. For the initialization, we're gonna define decoder embedding, and we're gonna use our decoder and our prediction head to predict the next token. And for prediction head, we need to put the number of tokens in the tokenizer as the last dimension, because we're gonna predict based on the maximum number of this last dimension and pick the token which has the maximum value. So that's why we need to set this last dimension as length tokenizer. And for our forward function, so for our other functions, we also have generate mask, which masks the future words of our input, so that for each token, it can only view the sequences in front of this certain token. It can't access the future ones because it needs to predict it. And for the forward function, we apply the mask to our target, and we put in the target into our decoder function. And then the decoder output is put into prediction head, which predicts the next token based on maximum value of each token index. So now that we defined our model, we can start training our model. So for the configurations, you can try modifying these configuration or using this default one. And we're initializing our GPT model, putting it into the GPU device, and we're going to use optimizer atom and cross entropy loss, which predicts the tokens. And we have our train valid data loader. So we defined our batch size as 64, and our 128 is our maximum sequence length. So this training code is the same for multiple lab sessions that we've went through, but it's a bit different here because we first generate the logits for the model output. And if we think about it, for the input, it starts with the begin of string token, and then it has all our real tokens, our real input tokens, and then our end of string token. But when we apply loss, we only the predicted output takes in the first begin of string and outputs the next token after the begin of string token. So that's why the target output should eliminate the first begin of string token in order to compute this loss by comparing the logits and target. And also for the logits, it generates the end of string, so we can eliminate that part too. And apply loss to these two by comparing these two, the actual target and the model predicted logits. And this part is also the same for evaluation. Oh, actually, for the logits part, It generates after the end of string token, so that's why we eliminate the last one. And then we can start training this code. And if you run the code, you can see that the loss decreases. And here for greedy decoding, I'll give you 5 minutes to implement the greedy decoding part. Okay. The GPT code. It's like this. I'll put it in the chat box. Oh, okay. This is too long, so I can't send it in the chat box, but we'll upload this solution file on Classroom today. And please implement this greedy decoding function here. You guys can capture screen if you want to for this GPT code here. So this is our greedy decode code, and we will loop through each input, and we will put the input into this model and get the output. And we can find the predicted words based on this last dimension, because as we defined in our transformer decoder part, in our GPT part, this last dimension is the length of the tokenizer. So we can predict next word, and we only need to get the last prediction, which is our target, and we can decode the results. So if we run this code, so this part, it concatenates the previous input and the predicted next word, and puts this into input again, and which is put through the model. And if the next word reaches the end of string, we can break. So before this lab session, I tried training this model and generating some results. So this is kind of like auto completion. And for a random test data sample, I took the first 20 tokens and predict the rest of the sequences using this greedy decoding. And if you train this model a bit more, you can get better results. And you can also try modifying the configurations. So you can try modifying the attention heads, or the dimension, or decoder layers, and check whether the loss decreases. And you can also check how the generated results get different based on different configurations. So this was the prompt that I put in, and it generated this part. Now we're going to start our second lab session, which is BERT. And BERT is a bidirectional encoder of transformer. So for GPT, it was decoder only based, but for BERT, it's encoder only model. And it's pre-trained using mass language modeling and next sentence prediction. For mass language modeling, it randomly masks tokens in a sequence, and based on the bidirectional attention, you need to predict the masked tokens. And for next sentence prediction, it predicts whether this certain sentence goes after this previous sentence. For BERT, it's an encoder-based model. So, oh, okay. Concatenation part for greedy decoding. So we take in the input, and then we have our predicted output here, which we only take the last word, and we concatenate this predicted next word and the previous inputs and put it into the model again. And this dimension -1, we get the maximum of this last dimension so that we can correctly predict the next word based on the length of tokenizer. And for Bert, so Bert uses bidirectional attention. So it looks for each token, it can view the previous sequence of tokens and also the future sequence of tokens. For causal language modeling and GPT, we cannot view the future tokens because we need to predict the next token. That is our job. But for BERT, it doesn't predict the next token. It only does prediction based on the whole sequence. So that's why it's okay to view the future tokens. And based on this bidirectional attention, we can do mass language modeling and next sentence prediction using BERT. So we're gonna do sentiment analysis with BERT today. First, you can import all the necessary packages, set the random seed, and we can start downloading our reviews.csv. It shows this data frame, and we can see that it has a number of rows of 12K and 12 number of columns. And then, so for this data frame, there is a column called score, and this is a review data with its review score, and we can view the histogram of the reviews in this data frame. So this is the score distribution. And then this toSentiment function here. So it would just kind of put these reviews into a three scale data so that it has negative, neutral, and positive. So if the rating is less or equal than 2, then it's negative. If the rating is 3, it's neutral, and otherwise it's positive. And if you plot this histogram again, you can see that these two are put together, these two are put together, and this is the neutral one. Okay, so for BERT, we're gonna use BERT base cased. We're gonna use the pre-trained model here. We're not gonna build a BERT model and train it from scratch, but we're gonna take a pre-trained model, which is open source already, and we're gonna utilize that pre-trained model. So that's why it's very important to use the tokenizer that the pre-trained model that we're using is tokenized based on. So if we run this code, it takes the tokenizer that was applied to our pre-trained model. And for this sample text, we can tokenize this text into tokens. So if we apply tokenizer.tokenize, it splits it into tokens. And tokenizer.convert tokens to IDs, it returns the token IDs. You can view the Hugging Face tokenizer documentation
for the functions that you want to use. And each tokenizer has different SEP tokens, CLS tokens, PAT tokens, or different special tokens. So that's why you can check it using this .sep token or .sep token ID. And then for encoding, you can use this encode plus method. So put in your input sample text and you can truncate the text if it exceeds this max length, 32. So we're going to set our max sequence length to 32 and then add special tokens and pad to this max length if the input is shorter than 32. So here we have our input IDs, which is padded until 32. And we also have an attention mask. And if we convert the IDs back to our tokens, we can see that our previous input has been encoded and then decoded again. So when it's encoded, it has this CLS, SEP, and PAD. And when it's decoded, it shows all these concatenated special tokens. So when you're fine-tuning a pre-trained model, it's important to consider their sequence length, the sequence length that the pre-trained model was trained on. So when we fine-tune the model, it should be less than the sequence length. It should be less or equal than the sequence length for the pre-trained model. And that's why we're gonna check our tokenized sequence length based on the data that we are trying to apply to this model. This is just to set up the sequence length for our data. So first we tokenize, so for this content column, we tokenized each data sample in this content column. And this tokens has the encoded tokens, which is max length 512. So 512 is the maximum length for most BERT models, but you can check for each model, it might have different max lengths. So whenever you're using a pre-trained model, you should always check the configuration file and check the max sequence length for the pre-trained model. And our data, we're gonna check the length for our data and put it into this list. And we can plot this token lengths list, which shows the distribution of the token lengths for our data. And based on this histogram, you can set the maximum sequence size. So we can use up to 512, but our data, it seems that most of our data is within maybe 160. It's safe to just use only up to 160 tokens as our maximum length because we have almost no data which is more than 160. And if we use maybe 512 as our maximum length, it would use up too much memory, which is unnecessary. So this is our dataset class. We have our reviews and our targets, and we can encode the reviews into tokens like we did before. And then just run this code. So, okay, this data set was modified, so it should be the number of rows. And we put in reviews, which is the content part of our data frame. So if we look at our data frame, we have content. And we have sentiment. So we can set it as our target. So we're basically predicting the sentiment. We're trying to predict the sentiment based on this reviews, the review targets, this of the reviews. And we're gonna use the pre-trained tokenizer and to encode our data with maximum length of 160. So if we look at the first data input IDs, we can see that it has the begin of string, the CLS token in front, added in front, and it's also padded until our max sequence length 160. And it also returns attention mask. So this encode plus returns input IDs and attention mask. And you can split the train and test data using this train test split. And you can additionally create a validation set by splitting this test data into valid and test. So just define the ratio for test size here. So for DF train valid test, this is the data shape. 13 is the number of columns for the data frame. And we can create a data loader by wrapping this dataset class into our data loader function. And we can set the batch size and number of workers for processing our data set. After defining this train valid test data, we can just wrap it using this function to return a train valid test data loader. We can view the first data for the train data loader, and it shows these keys. Okay, so input IDs, it's batch size 16 and sequence length, maximum sequence length padded to 160. And attention mask is the same, and the number of targets, it has 16 rows, 16 batches, so this is why 16. And now we're gonna load our pre-trained model from Hugging Face using this from pre-trained function. Again, it's very important to make sure that the tokenizer, if we're using the pre-trained weights of our pre-trained model, it's important to use the tokenizer that this model was tokenized on. So match the model for tokenizer and for the model. So we can have a look at this BERT model that we loaded. It has hidden state size of 132,768 and output size of 1768. So this is just the configuration of this BERT model. And for our sentiment classifier, we can use this BERT model. And because the return hidden state is 768, we need to put it through a linear layer, which outputs the number of classes. So outputs scores for each, outputs logits for each class. We can put our input data into this model with attention mask and get the output, and we can do some dropping and put this output through the linear layer. And this results in the last dimension as n classes. So we can put in the number of classes that we have when defining this sentiment classifier model instance and put the model to GPU. We can also put the input IDs and attention mask into the same device as the model. And then we can output the softmax of our input IDs and using the input IDs and attention mask. Okay, so the training down here, you can try by yourself because it's very similar to the previous lab sessions and also the GPT training. So there's train epoch and evaluation and testing. So you can try running this code down here by putting your device into GPU. And today, if you guys don't have any more final questions, I think we can end our lab session here. Do you have any questions? Okay, last hidden state size. Sequence length 32. Do you mean this one? Um, 1.32. Um, we need to look at the model inside. So we need to look at how each layer is defined into the BERT model. So that is why it's put into 32. You would have to look at the configurations. So when we put in this 16 times 160, we get this hidden state output, and this is different based on the model configurations. Default size. No, it's not default size. It's based on how the input is processed within this BERT model. So for GPT, we need to use embedding because we need to use it because we need to make the input into embeddings. So after we tokenize the inputs, we put it into embedding so that it's embedded into vector space. This decoder embedding is put into, are you talking about this part? Yeah, we need to put this into, we need to embed it in order to put the input through the model. This is actually different with positional embedding. Positional embedding is something added to the embeddings usually. Positional embedding is usually added to the embeddings, and it's something different with this embedding because this embedding embeds our input into embedding space. so that we can put it into the model, and we can add sinusoidal positional embedding to this NN.embedding. Yes, it is added in the decoder class here. So I got a direct message, sequence length 16. Okay, the sequence length sequence length is set to 16, and when we put in the input into the BERT model, based on the BERT model layers, the input is passed through the layers, and the output is generated based on the layers within the BERT model. So you would have to check the configurations for the BERT model. This BERT-based pre-trained model. Okay. I think we can end our lab session here. So, okay. Yeah. You guys can leave now.